In this screencast, we are going to talk about some of the chemical reactions that ketones and aldehydes can undergo, and then we're going to talk about some common ketones and aldehydes that you see in everyday life. So we learned in chapter 13 that when aldehydes are prepared by oxidizing primary alcohols, with things like potassium permanganate or potassium chromate, which we represent with this little O here, an oxidizing agent, the reaction continues to produce a carboxylic acid. Ketones are prepared similarly, but they're much less susceptible to further oxidation, especially using those mild oxidation agents. Now, this different reactivity here is one of the reasons that aldehydes and ketones are classified as separate families. So I want to show you some specific examples where, when we look here, so for example, this is benzaldehyde, and if benzaldehyde reacts with an oxidizing agent, what we're going to notice is that where there's that carbonyl right there, what we're going to see happen is that's going to be replaced by a OH. So we look at the carbonyl stays the same, but what gets replaced is, instead of a hydrogen there, now we're going to have an OH. And so we go from that aldehyde to carboxylic acid functional group. Likewise, when we look at a ketone, for example, if we look at acetone here, and we say, hey, look, does this undergo oxidation? There's no reaction because there's not a hydrogen there to be replaced. And so these are different functional groups, and they have different classifications because their reactivity, particularly with oxidation, is different. And so let's look at an example of what this would look like. When we look at these test tubes, what we have here is potassium chromate, which is what causes the oxidation. And then we have acetone here and benzaldehyde here. And remember, right, when we talk about acetone, that's a ketone. And in this test tube is an aldehyde. And we can see when we look at the next slide that this has stayed unreacted. So we've added the orange to this and nothing reacted there. When it does react and oxidizes, it turns this green color. So this is no reaction, and this is a reaction. And so that's the green color that it turns. Now, there are other oxidation reagents that we can use, and the effectiveness of these reagents depends on the ease of the oxidation of the aldehydes. So two of the reagents we're going to look at are Tollen's reagent and Benedict's reagent. And so when we look at these, they also both react with aldehydes. They tend not to react with ketones. When we talk about a Tollen's reagent, this is just a mild oxidizing agent that contains silver ions. And so what you will see here is a reaction that looks like this. You have an aldehyde. This is the Tollen's reagent. And it reacts in a basic environment. So that OH tells us that, hey, look, it's basic. And then it forms a carboxylate salt, and then you get silver metal here. One of the things that's neat about this particular reaction is that when this is carried out in a clean, grease-free glass container, metallic silver will deposit on the glass and it forms a mirror. And so this is used even now still commercially to silver mirrors or to give them that reflective surface. A big idea though here is that ketones do not react. The other reagent that we were going to talk about is Benedict's reagent. This reagent contains copper. So Benedict's reagent is just a mild oxidizing solution that contains Cu2+ ions. You can see here that it reacts with aldehydes. There's the copper 2+ from the Benedict's reagent. Now this is a blue in color. It also reacts in a basic environment to form a carboxylate ion and a brick red precipitate and then water. And so when you look at this here, right, and we look at the structural features, here we have an aldehyde with an adjacent carbonyl group, an aldehyde with an adjacent alcohol group, and a ketone with an adjacent alcohol group as well. Now, what's interesting about these groups is a lot of them are found in sugars, but these will all give a positive Benedict's test. Now, I want you to notice that when we talk about ketones, there's one type of ketone that will give a positive Benedict's test, and it's the one that's adjacent to the alcohol group. And so what that means is you have an alcohol on the carbon that's also directly attached to the carbon of the carbonyl. And what does a positive Benedict's test look like? When we look here, we've got a solution that's 5% glucose and then 2% glucose solution. These glucose is going to have, because it's a sugar, it's going to have functional groups that look like this. And so you can see here that you get kind of a brick red solution when it's very concentrated, and then you get kind of a brown solution when it's not very concentrated. And so that would be the color change you were looking for. If there was no change, it would just still be a blue solution. Now, another type of reaction that we've talked about before are addition reactions. And in chapter 12, we learned that addition reactions are common for compounds containing carbon-carbon double bonds. The same is true for this carbon double bonded oxygen of the carbonyl group in an aldehyde and in a ketone. And what you'll see here is the H2 will add across this double bond, and when it does, it adds one hydrogen to that carbon and then one hydrogen to the oxygen, and it gets rid of the double bond here. Same thing with a ketone. And so if you start with an aldehyde, you get a primary alcohol, and then if you start with a ketone, you get a secondary alcohol. I want to remind you that you can use the catalyst, either platinum or palladium. Both catalysts are used for this. So let's look at a specific example. For example, if you were asked to predict the product of this reaction here, what you would do is the very first thing is you would identify the carbonyl group here, and you would say, all right, that's what's going to react, and we're going to have this H2, and that H2 and platinum should tell you, look, this is going to be addition reaction. That's going to go away. The double bond is going to go away. And so what you would have is a CH3, a CH2, C will keep one bond to the oxygen because the double bond's gone away, and now we're going to add an additional hydrogen. And so we kept this hydrogen here, we've added a hydrogen here, and then we've added a hydrogen there. And so now we've made a primary alcohol. This is 1-propanol. Then when we come over here to acetone, which is a ketone, and we add hydrogen with platinum, again, when you solve problems like this, you need to identify where the carbonyl group is. That's the functional group there that's going to be the reactive center. And what's going to happen is when you add hydrogen, what you're going to see is that we have the CH3, that doesn't change, but the carbon that the carbonyl is attached to does change. The double bond goes away, and we're going to add 2 hydrogens. We're going to add 1 hydrogen to this carbon and 1 hydrogen to that oxygen. And so here, now we formed a secondary alcohol. So these are common addition reactions that we see. Now, aldehydes react with alcohols to form hemiacetals. Now, hemiacetals, right, are not very stable and really difficult to isolate. This is a functional group that's fairly important in carbohydrate chemistry, which we're going to get to in chapter 17. What a hemiacetal looks like is it's a carbon that's bonded to the OH that is also bonded to another oxygen that's bonded to an R group. And an R group just means the rest of the molecule or more carbons and hydrogens. So if we were to think about a specific example of this, we would have CH3, C, OH, O, CH3, H. And this is a hemiacetal because what we're looking at here is the OH here, this carbon, and there's an O and an R group there. And so this part here, which is the rest of the molecule, is just the R group. So it's a carbon that's attached to an alcohol and another oxygen. And when we get to the carbohydrates, we'll identify it as a carbon that's attached to 2 oxygens here, one of which is an alcohol. Now, a lot of times these can react again and form a more stable product called an acetal, where the OH is no longer there. Instead, you now have a carbon that's attached to 2 oxygens that are also attached to 2 R groups. A specific example of this would be CH3CH, OCH3, OCH3. So all we've done is, when we look at this functional group, is we've taken the hydroxide off. It's not there anymore. And this part would be the R, and this part would be the R corresponding to over here. And so they kind of look like diethers, right? Where you have 2 ether functional groups. But it's actually called an acetal. Now, when we talk about hemiacetal formation, what's happening here is we have a CH3 with a C double bond O and an H. And so we identify this as an aldehyde. And you react it with an alcohol. Now, when you react it with an alcohol, what you're going to see, and I'm going to break up and highlight our alcohol. I'm going to highlight this H as blue, and I'm going to highlight this CH3OH in yellow. And what we're going to see is that the H is going to attach to the oxygen, and then the OH attaches here. And so when we look at this now, it becomes CH3C. There's no longer a double bond, so this is an addition reaction. OH and OCH3H, where when we look at this, the yellow is here, and then the blue is there. And so you can see how that attaches. Now, I want us to look then at an acetal formation. When we look at an acetal formation, we start with a hemiacetal. So we're going to start with the hemiacetal that we just synthesized above. And we're going to add another alcohol. Okay. Now, it's important to know that this is happening in acid, so that's an acid catalyzed, so I'm going to show the H plus there. Another thing that you could see is like H2SO4. Okay, so either of those is an acid catalyst. And so again, I'm going to show, right, the CH3OH group here, okay? And what happens is, sorry, I'm fighting with colors, CH3, C, H, OCH3 doesn't change. The only thing that changes is now instead of having an alcohol group, you have a CH3 here. And what we know is that OCH3 comes from the alcohol. This OH and this H come together and form water. And so that's formed as a byproduct of this reaction. Now, ketones will also react with alcohols to form hemiketals, which here is the general formula of hemiketals. And in a very, like we mentioned before, in a very similar way to acetals, these will also react and form ketals as well. And so what's going on here is what differentiates them is that you started with a ketone, and then so instead of having a kind of an H here, you would have a C, but everything else is going to be very similar. So let's look at a ketone reaction. When we look at a ketone reaction, what we're going to see here is here's our ketone and here's the alcohol we're adding. We add the first R group here with the O, and there's two primes here, and it just says, hey, look, that's just R, that's the rest of the group, and it can be the same or different from this one. So we add it here, then we add another alcohol, and we can get a ketal carbon. So a hemiketal has the OH here, and there's two R groups here and an OR. A ketal has an OR here, an OR here, and then two R groups here. So let's look at a specific example. So there's our alcohol, which is ethanol. And when we look at this, and particularly when you start doing this, what you want to do is you want to identify that ketone. Ketone is there. When you look at that ketone, the next thing you're going to do is you're going to say, all right, let's draw the rest of the molecule. And when this goes through a reaction, the double bond goes away and we have an O here. And then what's going to happen is we're going to add a hydrogen here. And then what's going to happen here is we're going to add the O, CH2, CH3. So what you're adding here is anything that is attached to this oxygen, okay? So anything that's attached right there. Then what can happen next, right, is that this can go on and react with another molecule of the ethanol, the CH3, CH2, OH, and this part of the molecule will attach where the OH is. And so you end up with CH3, C, CH3, O, CH2, CH3, and that was a really wild bond, so I want to kind of fix it. Then over here, O, CH2, CH3, where whatever is attached to that oxygen is what you have show up here. Now, again, just like on the previous slide, what we're going to see here is that the OH that's here and the hydrogen that are here go to form water. Okay. So those are both acetal and ketone reactions that we see. Now, one of the things that we see is that some molecules contain both OH and C double bond O groups on different carbon atoms. And so in this case, what can happen, right, is you can have an intramolecular reaction. And an intramolecular reaction just means that it's happening, the reaction happens within the molecule, right? And so when this happens, that's where you would get a cyclic hemiacetal or a hemiketal conformed. When we look at identifying this functional group as a hemiacetal, you find this carbon here, and you notice that it's attached to an oxygen and an OH group right here. It also has, like, this would be an R group, but we're looking for the carbon that's attached to the oxygen and an OH group. And so that would be a hemiacetal. You can see another example of the hemiacetal drawn here. And when we look at the cyclic acetal or the complete acetal, again, what we're looking at here is this carbon right here, and now it's bonded here and here. And so we can see both of these. Now, I want to point this out because we're going to study these more in chapter 17 in sugars. And so, for example, like glucose and fructose exist predominantly as these cyclic hemiacetals and hemiketals. Now, in another kind of map that we have, so previously we've talked about reaction maps that are really helpful. We now can add to our reaction maps. We have aldehyde or ketone here. They can go through oxidation reactions, and if it's an aldehyde, it forms a carboxylic acid. If it's a ketone, there's no reaction. If it undergoes hydrogenation, it can form a primary alcohol or a secondary alcohol. If it's a ketone, primary if it's an aldehyde. If you have an aldehyde or ketone that reacts with an alcohol, it can form a hemiacetal or a hemiketal and then react again to form an acetal and a ketal. So that's a really great summary of the things that we have learned. Now, one of the things to be aware of is that the acetal and ketals are stable, but they can be converted back to aldehydes and ketones through acid-catalyzed hydrolysis. So hydrolysis is just bond breakage by a reaction with water. And so what happens here is that acetals and ketals are converted back to aldehydes and ketones. And so here's a general reaction for the acetal hydrolysis. You have an acetal here, you add water with a little bit of an acid, right? And what happens here is now we end up back with our double bond here, right? And we've lost the R group here and the OR group here. And those instead come to form the two alcohol groups here. So it's just the reverse of that reaction. This type of reaction causes the compound to split back into its component substances by adding water, and that's why it is called hydrolysis. And I like to think about it, you want to be really hydrated. That's where the hydro comes from. And then lysis here means to break apart. And so you're breaking things apart with water. So it's just a helpful kind of mnemonic. So let's look at that a little bit more closely. Here's the general reaction for ketal hydrolysis. If we wanted to look at a specific example like this, CH3, CO, CH2, CH3, O, CH2, CH3, we would add water. And the first thing you would need to do is you would need to come in here and identify, and I left out a CH3 right there. you're going to need to identify the carbon that's attached to the two oxygens, which is right here. And what's going to happen then is, instead of having the carbon that's attached to the two oxygens, what you're going to have instead is just a C double bond O. And then these groups here, right, that's what's going to give you your clue as to what's going to be your alcohol. So we would form two CH3 CH2 OH molecules from the alcohol that we would see there. Now, I want us to do another example. So this says, draw the structural formula for the products of the following reaction. Now, first off, you need to identify what your reactant is. When we look at this reaction, there's a carbon here, and it's attached to an oxygen that's an OH here, and another O that's then attached to an R group here. So you should be able to identify that this is a hemi ketal, because there's the R group here and then there's the R group here. If it was a hemiacetal, one of those would be a hydrogen. You can see we're going to add an alcohol and the H plus here. And so when we look at this, what we're going to know is that this is going to replace the OH. So then when we draw our product, that would be our product, and we would make water. Now, that would be it for our aldehyde and ketone reactions. We're going to end this chapter by talking about a few important aldehydes and ketones. Formaldehyde is it's the simplest aldehyde. I have the structure here shown for you. It's a gas at room temperature, and it's most commonly supplied and used as formalin, which is a 37% aqueous solution. And an aqueous solution just means that it's mixed with water. So you have a solution that's 37% formaldehyde, and then the rest is water. This is used to kill microorganisms. And sterilize surgical equipment. It's also used in embalming fluid, and you might have most often seen it because it's also used to keep specimens such as frogs in jars from decomposing. It's also a key chemical in industry to help in the production of plastics like formica or bakelite. An important ketone is acetone. This is a really important solvent. It's used quite frequently as a solvent, right? And it's widely used as a solvent for coatings, but it can also be used in fingernail polish, which is where I would think you would run into it also most frequently. There are many naturally occurring aldehydes and ketones. A really great example of some of these is hormones that are found in the body. So, for example, you've got progesterone, which has a functional group here, right, that is the carbonyl group, as well as a carbonyl group here. So this has a ketone, and testosterone also contains a ketone here. So these are female, male, and sex hormones, and they're found in nature, as well as many of our sugars, which we talked about, but we also have some fragrant aldehydes and ketones. These are things like vanillin, cinnamon, citral, which is found in limes and lemons. This is butter flavoring, which I pointed out at the beginning. This is camphor. That kind of gives us a medicinal odor. It's an ingredient in some inhalants. And then menthone, which is in mint plants. So aldehydes and ketones are also, we run into these quite frequently if we're cooking or using perfumes or things like that. So this for us ends chapter 14. As always, if you have any questions, please feel free to stop by my office.